So in continuation of our lecture 6, we are discussing about the rectangular fins. So in the lecture 6 we have discussed that the fins have many applications that avoid any particular equipment for overheating, and at the base of or at the body of the equipment the fin is connected in such a way that extended surfaces are provided, and when air is in contact with this particular extended surface, then additional heat is convected away and cools the temperature of the body of that equipment. So now if we take a rectangular fin, this is a rectangular fin. So here we are trying to find the general expression how the temperature is varying in a rectangular fin when it is connected, suppose it is connected a body of equipment. Suppose this is a body particular, this is the body of the equipment, and this rectangular fin is connected in such a way that whenever heat is conducted through this is convected away by the convection. So first we have to see about the how this diagram is look like and how the fin is. Suppose the fin is of length L connected at the body of the equipment which is heated surface at temperature T0. Now this is the cross section of the particular, this is the cross section of the rectangular fin. When air heat is conducted through the body by conduction, it go normal direction, and you can say that it is going to x direction only, and it is crosses all across this particular cross sectional area. So heat going to enter here, enter at the base of this particular fin and come out only in x direction by pure conduction. But when heat is enter inside this particular rectangular fin, then this surface is get heated, and when the surface is get heated, then air above this particular rectangular fin try to convect the heat or temperature. Because of high temperature is maintained here due to this conduction, then all the heat is can be convected by the air outside it. So this is very simple, that heat is entering at the base of the rectangular fin and convected away when air is exposed over this particular surface. So you imagine this is assume the perimeter. What do you mean by perimeter? Suppose at any distance x we have taken a perimeter of thickness dx. What is perimeter? If you see this particular rectangular fin from this side, you see such types of cross sectional area with thickness dx, and this length is z. So our perimeter is nothing but 2z plus t, or 2z plus 2t. Why so? Because if you see from that side this fin, you see a simple cross section like this way, this cross section having length z and thickness t. So this is our perimeter. So what is the area of this perimeter? This particular, if perimeter is this p, then if you multiply p with dx, you got the area of this particular cross section, and this area is only exposed to the air, this side and the similar at the back side of this and this particular region, and one is the opposite of that. So you can see the four walls are like this, and this the area exposed for the convection. So in this way we can now apply energy balance for a rectangular fin. So if we write down the energy balance, then the statement of energy balance will be like energy conducted through the left surface, the left face, equal to energy out by conduction at right face plus energy lost by convection. Energy lost by convection. This is our simple statement of energy balance by conduction. So whatever energy conducted through this particular volume element, you can say this particular region, if you tilt like this way, if you tilt, it is just the front view. If you tilt it like this way, then you find the same. If you tilt like this way, you find the same with the z length is z and thickness is dx, and you find the perimeter is like, for particular this region, this element is p 2z plus 2t, but here if you want to find out the area, then p into dx will be the area of this particular cross section. So this area is only available for the convection through this element. So we are applying energy balance only this perimeter only. So that's why we are writing this energy balance like this. So now we are moving forward. The mathematical form of this energy balance can be written as whatever conducted at the left face is qx. So qx equal to q x plus dx plus energy lost by convection, because whenever heat keep on flowing and coming out from this cross sectional area, this surface, the entire surface from the upside and bottom sides get heated, and when it is get heated, its temperature will be higher than environment, and then convection is taking place. So whatever energy is conducted by the conduction is convected away. So you can see either entering energy is either is conducted by the outer surface or lost by convection. Only two possibilities: whatever heat is conducted inside this particular rectangular fin and coming out from this cross sectional area A, then either entering heat is either conducted from this particular cross sectional area or lost by this convection process. So only two possibilities for the entering heat. So what is entered here is either conducted away or lost by convection, and when you talk about what is lost by convection, you can write h air into cross sectional area, that is p dx into t minus t infinity. Why p dx? The question is why p dx? So if you see the diagram clearly, if you see the diagram like this, if you see the diagram, you know that if you apply energy balance through this particular element, so its perimeter is nothing but p and thickness is dx. So how much amount, how much area exposed for convection? This particular area and this particular area. And if you calculate this particular area, you can write the P into dx, where P is nothing but length of this and this. Suppose this is Z, then P equal to Z plus thickness, but it is from the both side, the top surface and the bottom surface are similar, so it is multiplied by 2. So this is our perimeter into dx. So this particular value, or P into dx, define the area for this region, and to the same surface on the opposite side. So that's why the area for convection is involved is P dx here. So that's why we can say that our energy balance mathematical expression is look like this, where H is heat transfer coefficient for the air, and if the at any time t, if temperature is maintained for that particular element is T, and T infinity is the temperature of air, then you can write the energy balance like this way. Now we know that it is nothing written by, because the heat is by conduction, you can write down Ka dt by dx at x equal to minus Ka dt by dx at x plus dx plus h air into P dx into T minus T infinity. Now A is the cross sectional area. A is the this cross sectional area, this particular, because this is available area for the conduction only. So that's why we have write down this. Now if you take this particular value in the left hand side, you get Ka dt by dx at x plus del x dx minus Ka dt by dx at x equal to hp dx h air T minus T infinity. Now we divide both sides by dx, so we remove dx here and divide this side. Now it is differential change in value of qx over the length dx, so it can be written as minus d by dx minus Ka dt by dx equal to h into P, h air into P into T minus T infinity. If we imagine, or if you see, if T minus T infinity is written as any different symbol, that is theta, then we can write down d by dx to minus K a d theta by dx equal to h air into P into theta. If theta is T minus T, so then d theta by dx is simply is nothing but dt by dx. So that's why we can replace this dt by dx here, and we can write this way. If K is constant and area for the rectangular fin is also constant, because a rectangular fin have definite dimension, then you can write down this particular as minus d2 theta by dx2 minus h air P by Ka into theta equal to 0. Or you can say that and you can say that this value is nothing but so first we write down this value. This is this value is now positive when come to this side. This is k dt by, sorry, you make a little correction here because this value is positive now, because this is greater value than this one, so that's why this differential equation is positive, and we write positive symbol here, or it is not required. So this is nothing but this equal to 0. Now this is our desired expression. Now it is second order differential equation. For more realistic form, you can write it as d2 theta by dx2 minus m square theta equal to 0. Why so? Where m is root h air p by k a. So this is second order differential equation. To solve temperature at any distance x, you have to solve this differential equation, and we know that for solving any differential equation of second order, we need at least two boundary conditions. So here still we need two boundary conditions. So we are discuss some case, and for the different cases the boundary conditions will be changed for this differential equation, and we have three cases so that we can obtain boundary condition using these cases to solve this differential equation. The first condition is if fin is very long. Case 1 is fin is of infinite length, and at x equal to infinite, t equal to t infinity. So in this case we assume that the fin is so long that at x equal to infinite, at infinite length from the base of the body, or you can say the body temperature at x equal to, there is no effect of the wall of that particular equipment, and hence the temperature at infinite distance is same as temperature of air. So you can say if fin is very long, suppose for the case if fin is infinitely length, then what happen, then this temperature will not affect at the infinite distance, and this temperature of this particular surface is same as the temperature of air. This is the first case. Second case is fin is of finite length and heat loss by convection at the end. At the end of the fin. So if our fin is like this, and you say that whatever heat is entering here, then this is length is finite, and whatever temperature is here, heat is convected away from this surface. So fin is of finite length and heat loss is by convection at the end of the fin. So here convection is also involved along with conduction at the end of the fin. So this is case 2. And the case 3 is the fin is insulated at x equal to L. So dt by dx is 0 at x equal to L. So if we concentrate on these 3 cases, we find that each case is providing 2 boundary conditions. Each case is providing 2 boundary conditions to solve this problem. How? Because at t equal to t0 at x equal to 0 is already maintained, because we have said in the starting of the chapter that at the base the temperature is T0 at x equal to 0. So this boundary condition is always remains same for each case, and second boundary condition is achieved by these statements. So for example, for case 1, first boundary condition is this and second is this. Similarly for case 2, first boundary condition is this and second is by this statement. Similarly for case 3, first boundary condition is this and third boundary condition is given here. Now we will try to find out what is the solution of this differential equation where theta is t minus t infinity. So let's take case 1 by 1. So here first we take case 1 when fin is of infinite length and at x equal to infinity temperature is essentially as equal to temperature of environment or air. You can also say this condition as fin is so long that essentially at end of the tip of that particular fin the temperature effect at the x equal to 0 is not reaching there, and temperature of that particular tip is equal to whatever the temperature of environment. So this is the case 1. So now come to our particular mathematical expression of energy balance. d2 theta by dxt minus m square theta equal to 0. You know how to solve this. This can be written as from mathematics d square minus m square equal to 0 or d equal to plus minus x m, and we can write the solution directly for this, that theta is nothing but c1 e power mx plus c2 e power minus mx. We solve this differential equation by second order differential equation in this way, and we know that how to solve the particular integral and for this particular, and so the direct result for this kind of second order differential equation is c1 e power mx plus c2 e power minus mx. Now apply our boundary conditions what is given at the initially. Boundary condition 1, at x equal to 0 theta equal to theta naught. Why? Because theta equal to nothing but t minus t infinity, and at x equal to 0 t is t naught. So we can say that theta equal to t naught minus t infinity, and this we assume as theta naught. So theta naught is nothing but t naught minus. So we can say that at x equal to 0 theta naught is c1 e power 0 plus c2 e power 0, or we can say that theta naught is nothing but c1 plus C2. This is our desired expression for boundary condition 1. Now if we consider the boundary condition 2, given that theta equal to C1 e power mx plus C2 e power minus mx, then second condition for case 1 is the statement that is given the fin is so infinite or infinitely long that at the end of the tip of the fin temperature is essentially equal to the temperature of environment or temperature of fluid that surrounds that particular fin. So now you can say that if we assume theta equal to t minus t infinity, then you can see that at when this t equal to infinity t infinity, then theta equal to 0 at x equal to infinite. So at x equal to infinite, this t equal to t infinite and theta becomes 0. So when we put this infinite, this becomes essentially 0. But in particular case, if we see, if we put infinite value, this becomes infinite. So it cannot be infinite. So in that particular case, C1 must be 0. So C1 must be 0 because this theta cannot reaches to infinite. So C1 is 0 from the statement of boundary condition 2. So now you can say that 0 equal to C2 C1 must be 0. Now we have seen that C1 is 0 and our first statement is theta naught equal to C1 plus C2. So we come to the conclusion that theta naught equal to C2 plus C1, but C1 is 0, then C2 equal to theta naught. This is from our boundary condition 2. Now with the boundary condition 2 is this, so we can now put theta equal to C1 e power mx, so C1 is 0 plus C2 is theta naught e power minus mx. Theta naught, C2 is theta naught. Now you can say that theta by theta naught equal to e power minus mx. Or in temperature form you can write T minus T infinity divided by T naught minus T infinity equal to e power minus mx. So this is our desired result. So whenever there is a rectangular fin of infinite length at any distance L or x, you can find the temperature using this formula. Now satisfying your both boundary conditions here, otherwise this particular statement not correct if it is not satisfying the both boundary conditions. Our first boundary condition is saying that at x equal to 0 temperature is T naught. Now you can see if x equal to 0, then it becomes 1 and infinite is cancelled out on T equal to T naught. So first boundary condition is satisfied using this relation. So this relation is correct for boundary condition 1. Now checking for the boundary condition 2. If x equal to infinite, this becomes 0. It becomes 0, then this becomes multiplied 0 and t equal to t infinity. So both boundary conditions is satisfied. So you can say that this particular expression for finding out temperature at any time distance x in a rectangular fin is correct. So you can say that for case 1 theta equal to theta naught e power minus mx or theta by theta naught equal to e power minus mx. The both conditions are correct. Now if you want to find out heat lost by fin, then you have to calculate what amount of energy is conducted at the base of the fin. So you can say the heat loss is nothing but what is conducted at the base of the fin, because whatever the heat is conducted from the base of the, it either conducted through the if suppose for example this is our fin, whatever heat is conducted here is either lost by conduction through this cross section or convected away by convection. So either conduction, either convection, two mode of loss, but this amount, whatever amount of heat is q at x equal to 0. So we are total heat loss by the fin is calculated at the base of the particular fin. So if we know that t minus t infinity equal to t naught minus t infinity e power minus mx, so by calculating this you can write down ka dt by dx. dt by dx is nothing but minus m t naught minus t infinity into e power minus mx at x equal to 0. Now this becomes positive, and if you put x equal to 0 here, you will get ka m theta naught, because t naught minus t infinity is theta naught. So this is our desired, or if we put this value of m root hp upon k, so it becomes root hp ka into theta naught. How it is? Because when you multiply this k with m, ka into root hp upon k, so this will cancel out by this particular, and root k is left here, that is multiplied inside, and we will get this value. So the heat lost for a fin of infinite length is this particular value. Now we have seen for the case 1, theta is this and heat loss is this value. Now we are taking case 2. Always remember, the first boundary condition is initially given that at the base of the fin temperature is T naught is maintained, and that T naught is nothing the temperature of the body of that equipment in which this fin is attached. So that's why if we take case 2, remember the statement of case 2. For case 2, the fin is of finite length, and heat loss is by convection at the end of the fin. So what it is saying is like this. Suppose it is our fin, suppose this is our fin, you can say, and this is length is L. So it is saying that whatever heat is conducted here is just lost by convection as well as conduction at the end of this tip of the fin. So this is our desired sample. Now again we are recalling our expression that d2 theta by dx2 minus m square theta equal to 0, or theta equal to c1 e power mx plus c2 e power minus mx. This is our desired expression. Now first boundary condition is also maintained. Again at the base of the fin temperature is T naught, so theta naught equal to C1 plus C2. This condition will always in all three cases, but the second case is now changed. It is saying that at x equal to L, whatever is heat is conducted at x equal to L is by convection. So whatever heat is conducted at L is equal to lost by convection. So you can say that H into P into L T minus T infinity at x equal to L. This is saying, this is a statement that at the end of the fin heat is lost by convection. So at x equal to 1, whatever the heat is conducted, for example if we see the fin, whatever at the x at L, what is the heat is conducted is removed by convection. This is the statement. So now if we solve this problem, we put boundary condition one by one. So from first boundary condition we already found that theta naught is C1 plus C2. This is condition 1. This is boundary condition 1, and we find this theta naught is C1 plus C2. Now for the second boundary condition, minus Ka dt by dx at x equal to L equal to HPL, this is H air, not confused about that, T minus T infinity. Now our minus Ka, if you differentiate this value, that T minus T naught T infinity upon T naught minus T infinity, theta is given like this, C1 e power mx plus C2 e power minus mx. It is nothing but theta. So if you differentiate this, you will get differentiation of this. So you can write differentiation at x equal to L is equal to mc1, differentiating this to find dt by dx at x equal to L. So you will get this value mc1 e power mx minus mc2 e power minus mx. But this condition at x equal to L, you can directly put x equal to L here, x equal to L, it becomes x equal to L. So if you put x equal to L here, you get e power ml minus mc2 e power minus ml into k. This is our left side. What is our right side? H air into P into L. This is our T minus T infinity at x equal to T is minus T infinity So you can directly write as t minus t at L. So t at L, t minus t infinity at L directly can write as t minus t infinity at x equal to L. And we know that what is t minus t infinity. So if we put this value at L, this is the value. Now further saying that minus ka mc1 e power ml plus minus mc2 e power plus ml, oh sorry, minus ml, because we have taken this ml, this is minus ml, equal to h air h8p into L into c1 e power ml plus c2 e power minus ml. This is the case. Why so? Because t minus t infinity is nothing but theta, and theta at any x is c1 e power mx plus c2 e power minus mx, but at x equal to L we can replace x by L in the expression of theta. So this is our desired result. So in previous case you can write this statement also as in terms of theta, so that there will be no confusion. Ka d theta by dx at x equal to L equal to hpl theta. So where theta is t minus t infinity. So this is the case. Now our this is equation suppose 2. What is our equation is theta naught equal to c1 plus c2, or t minus t naught minus t infinity is equal to c1 plus c2. This is our from boundary condition 1. So we have two equations, one from the first boundary condition and second from the second boundary condition. Now you have to find out c1 and c2. Now how you will find out c1 and c2? Solve this one and find out c1 and c2. If you solve this, you will find that c1 equal to, because the long relation, try it your by own so that you can get this complicated relation. It becomes theta naught 1 minus h by km e power minus ml divided by 1 plus h by km e power ml plus 1 minus h by km e power minus ml. This is the value of c1. Again for c2 is theta naught 1 plus h by km e power ml divided by 1 plus h by km, denominator is same in both cases, h by km e power minus ml. So when you solve the both equation 1 and 2, you will get this c1 and c2, where theta is nothing but t naught minus t infinity. Theta is nothing but t naught minus t infinity. So if put in general equation that theta is any distance x is c1 e power mx plus c2 e power minus mx, and you put these two c1 and c2 in that expression, you will get theta by theta naught equal to cos h hyperbolic function m l minus x plus h by mk sine hyperbolic m l minus x divided by cos h ml h by mk sine h ml. This will be our desired expression, that is nothing but t minus t infinity upon t naught minus t infinity equal to this. So in case of a finite length fin in which at the end of the fin at x equal to L, heat is convected or heat is lost by convection only, is given by this formula. So see how the complicated this particular. Now if you find out Q loss by the fin, then you can say there are two methods to find out the Q loss. One way is find Q loss at the end of the fin, that is simply you can calculate HPL theta at x equal to L. Either you calculate this, because whatever the heat is conducted is just lost at the end of the fin is by convection. One way is this. Another way is very simple. Whatever heat is just entered at the fin from the base, so either you differentiate it and put this value, either you will simply put theta at x equal to L. By putting this and this one, you will get that. So this is easy method. Why so? Because if you calculate this Q loss at the base, you have to differentiate it. And now if you want to theta at x equal to L, then you simply put x equal to L here and L here. So you will find out that when you put x equal to L here, then this becomes cos h m L minus L cos 0 h by mk. This becomes sin h 0 upon this value. So in this way, if you put theta at x equal to you will get theta naught and this whole value will be such that, so this becomes or if you find this Q loss by this formula, if we differentiate it, this becomes sin h m L minus x plus h m upon k cos h m L minus x, and that particular case when put x equal to 0, then in that particular case the same expression will be obtained, this and this. So when you calculate this Q loss, you will find, so first differentiate this. First you are applying by using this formula. Q loss will minus Ka into differentiation of this particular. So when you differentiate cos hyperbolic function, it becomes sine hyperbolic, and at x equal to 0 it will be sine hyperbolic ml, because when differentiate it, it becomes sine hyper, or when you put x equal to 0, it becomes sine hml. Now again h by mk. If you differentiate, it becomes cos h hyperbolic, cos hyperbolic ml minus x, and again if put x equal to 0, it becomes cos h ml. And this particular cos h ml plus h by mk sine h ml. This is our Q loss. Now putting this value of Ka, this is our, but whenever you differentiate it, m is multiplying inside, this will come outside, and you will like this, you will get like this. And this particular, this is only dt by dx. So if you differentiate L minus x, then minus comes sign here. Here also you are differentiating L minus x, then sign, minus sign will come out here. And this whole differentiation multiplied with theta naught, because you are differentiating only t minus t infinity. So whatever multiplied with theta naught, because you are just differentiating t minus t infinity, so t naught minus t infinity go that side, and you will get the final expression like q equal to m k a. Now whole expression sine h ml plus h by km cos h ml divided by cos h ml plus h by km sin h ml. Km is nothing but root hp by k into k, and with desired expression. So you can say, write down k, root of this becomes root hp upon hpk. So in place of this mk, you can direct push this value, and you can write down this is root hpka. This is Q loss in case of case 2. This expression. So in this case we have found two relations. First is theta by theta naught is cos h m l minus x plus h by mk sin h m l minus x divided by cos h ml plus h by mk sin h ml. This is our first relation, and second relation is this Q loss is equal to root hpk into this particular sin h ml plus h by mk cos h ml divided by cos h ml plus h by mk sin h ml. So these are two results that is obtained. For the fin is of finite length and heat loss is by convection at the end of the tip of a rectangular fin. So this is our case 2. Now moving forward for our case 3. For case 3, the statement was fin is insulated at x equal to L, or if there is a fin like this, fin is insulated here at the tip at x equal to L, the fin is insulated. And we know that whenever the fin is insulated, dt by dx is 0 at x equal to L, because we know the condition of insulating wall, that there is no conduction of heat there. So whatever heat is entering inside could not conduct here. Now we know that theta is c1 e power mx plus c2 e power minus mx. So in case of solving second order differential equation in case of rectangular fin by energy balance, where theta is nothing but t minus t infinity. This is the statement we obtain from differential equation. Now again the first boundary condition will be same. At the base of the tip, temperature is T naught. So at x equal to 0, temperature is T naught, and we get theta equal to C1 plus C2. Theta naught equal to C1 plus C2, because where theta naught is T naught minus T infinity. Because when x equal to 0, this is the x equal to 0, then theta naught equal to C1 plus C2. Because theta is theta naught at x equal to 0, so we are putting x equal to 0 and temperature as theta naught, then becomes. But the second condition is because of this particular statement, because we have earlier discussed that whenever there are two second order differential equation, we need two boundary conditions to solve such types of problem. And this is a steady state problem with no heat generation or something like that. In that particular, we have a second order differential equation and there are two boundary conditions. One is from given that at x equal to 0, t equal to t naught, but we are discussing in case 3, the second boundary condition will come with the statement of case 3. Now at x equal to L, dt by dx is 0, it is given. Now, or you can say that this is d theta by dx is 0. Why so? Because theta is nothing but t minus t infinity. When we differentiate this t minus, then becomes d theta by dx equal to 0. Now differentiating it d theta by dx, we will get mc1 e power mx minus mc2 e power mx. Now at x equal to L, then this replaced by L, so at x equal to L, d theta by dx at x equal to L, it becomes mc1 e power ml minus mc2 e power ml minus ml, sorry, minus ml equal to 0. This is condition given at the tip of the fin, that the fin is insulated. Now we are reaching at the two equation again. First equation is theta naught is c1 plus c2, and second is mc1 e power ml minus mc2 e power minus ml is equal to 0 from the second. Now we have to find out c1 and c2 here. Again in this case m got cancelled out both sides, so we will find simply c e power ml equal to c2 e power minus ml, and yeah, or you can say that c2 is c1 e power 2 ml, and also we now know that theta naught is c1 plus c2. Using both equations you can find out c1 and c2. If we put this value of c2 here, c1 plus c1 e power 2 ml, so or in case c1 is theta naught 1 plus e power 2 ml. Or in particular it can be written as theta naught e power minus ml e power minus ml e power ml sorry e power minus ml plus e power ml. Can we write this in this way? No, we can't. We can write it like this way, because when we divide e power ml minus ml in both numerator and denominator, you will get the same value. So c1 can be written as, you can say c1 is nothing but theta naught e power minus ml e power minus ml plus e power ml, but c1 plus c2 is c theta naught. Now c2 is theta naught minus c1 or theta naught minus c1, theta naught e power minus ml e power minus ml plus e per ml, and then you get c2 is theta naught e power ml e power minus ml plus e power ml. Since our general expression is theta equal to c1 e power mx c2 e power minus mx, and if we put this c1 c2, c1 is obtained by this relation, if we put there, then we get theta equal to theta naught e power minus ml e power mx plus theta naught e power ml c2 value e power minus mx divided by, because denominator is same, this is our desired relation. Now if we take theta naught this side, you will get theta by theta naught equal to this value equal to e power, if you take minus m outside, it becomes L minus x, and if you take m outside, then it becomes L minus x e power minus ml plus e power ml. You can just this way can be also written, because here e power ml is written first, but here we are written afterward, so nothing is different. So our theta by theta naught becomes, what is this value? Cos HML minus x. What is this value? Cos HML, because when it is both are divided by 2, numerator and denominator, this is the formula of cos HML. So it is cos HML minus x, cos HML. This is our desired temperature distribution function in case of case 3, where fin is insulated. Now whenever you want to find out that what is Q loss, again you have calculated K A d theta by dx, or K dt by dx, or because theta is t minus t infinity, so you can directly K A d theta by at x equal to 0. This is our Q loss. So because theta is, in this case, is theta naught cos HML minus x upon cos HML, whenever you differentiate this value, d theta by dx is nothing but theta naught, this becomes sine HML minus x, because of minus L minus x differentiated, so minus is here, divided by cos HML at x equal to 0. When you put x equal to 0, it becomes minus tan HML to theta naught. When you put this in this relation, then Q loss equal to K A theta naught tan HML. This is our desired value of Q loss in case of case 3. So we have discussed 3 cases. Here theta equal to theta naught, this value for temperature. Whenever you want to find out the temperature at any distance x, you can put t minus t infinity here, t naught minus t infinity here. You will get this value at any distance x. So these are the 3 relations, 3 cases we have discussed to find it out the temperature and Q loss for the rectangular fin. Now we will discuss the 2 terms that are frequently asked in the GATE examination, that fin efficiency, first at fin efficiency, and fin effectiveness. We define both terms by simple definition, fin efficiency and fin effectiveness. Simple definition is actual heat transfer to the ideal condition. What will be the ideal condition? Suppose if it is a fin, this is the suppose fin, suppose this is our fin, and here the temperature is T naught and here is temperature is T. Then it is saying that fin efficiency is actual heat transfer through the fin. It is nothing but Ka x equal to 0, actual heat transfer, then the efficiency is something divided by the ideal condition. What is ideal condition? When if conducting material or fin is made of such a material that thermal conductivity is very high, you can say infinite conductivity, then in that case whatever temperature is here, there is no temperature gradient in the fin, and the whole base of the fin reaches as the temperature T0. Because when the conductivity of this particular rectangular fin material is so high, then as soon as the body temperature reaches T0, the whole fin reaches as T0, and whole temperature if T0, then more driving force is available for the convection. So this is the our ideal condition. So ideal condition is heat transfer when entire fin at base temperature. So what is actual heat transfer depend upon either case 1, case 2 or case 3, depend upon the case, because we have seen that in each case actual heat transfer is different, because that is calculated by this formula. And if the whole fin at the base temperature, then in the ideal case the total heat transfer is HPL T0 minus T infinity, because in that particular case the temperature of at any distance x is T0, because fin is of infinite conductance. When the conductivity is so high, then always the fin base is at temperature T0. So this is our fin efficiency. For example, if we take case 1, for example, if you take case 1 where fin is of infinite length, then what was the actual heat transfer in that particular case? In that case the Q was K root HPKA into T0 minus T infinity. This is the case 1. And if we put this value here for case 1, the fin efficiency becomes root HPKA T0 minus T infinity divided by HPL T0 minus T infinity. And that particular case, you find that this ought to be, when you divide such a thing, you find 1 upon ml, where m is nothing but root hp upon k. This is for case 1, because for case 1 actual heat transfer is this. When you find for case 1 this value, this becomes this, and when you calculate the efficiency, put actual heat transfer, that is this, divided by when entire fin at the base temperature. It means whenever the heat is convected away, the all surfaces at the base temperature, that is T0, and this will happen. And we find that, so you can say that for case 1 you can say that effectiveness is 1 upon ml, or this m is root hp upon k, so you can write down k by hp into L. So this is where P is nothing but 2z plus 2t. Again for case 2, actual heat transfer, that is K dt by dx at x equal to 0. This is actual heat transfer. So that particular big relation, that is root HPK theta naught into sine H ml plus H by km mk cos H ml divided by cos H ml plus H by mk sin H ml upon actual heat on in ideal case it is nothing but HPL T naught minus T infinity, or it is also theta naught. And similarly for case 3, we know that efficiency is in case 3 we found that actual heat transfer was tan H ml theta naught divided by HPL theta naught and we find that this is nothing but tan H ml upon ml. This is for case 3. Temperature Q loss is K tan Q loss is K dt by dx. This is M. Because whenever you just differentiate it, you get this value M. So this is Q loss in case of case 3. So whenever you find this case 3, write down this is actual heat transfer is nothing but K M theta naught tan H ml and actual is HPL theta naught. When you will find this value is nothing but tan H ml upon ml, because M is HP by K. So this is the value. So we have seen in all those 3 cases what is actually the fin efficiency is. Now if we discuss about the fin effectiveness case, fin effectiveness, how effective the fin is, then in particular case we can say then effectivity of fin is given by heat transfer when there is a fin and heat transfer without fin. If suppose there is no fin, only this equipment wall is this, and temperature maintained is T0, then heat is always by convection at the surface of this particular body of the equipment. But if that fin is attached, in the same case, if fin is attached like this, then how much heat transfer is improved because of this fin. So you can calculate E fin is obviously heat loss in case less than this case, so it is Q with fin and Q without fin. So Q loss will be more in that with fin, but without fin it is less. So this is our formula, and when you will find the fin effectiveness, so there is formula for finding out if for case 1, case 2 or case 3. So without fin it is well known, because when there is without fin, then whatever heat is HA delta T, HA T naught minus T infinity, because whatever, if there is a cross sectional area is like this A for the body, you can say if the cross sectional area is this and fin is not attached, suppose afterwards fin is attached to this area, but if there was no fin, this cross sectional area is exposed to the air, and you can say that if the base temperature is T0, the driving force is T0 minus T infinity for outside air, and you without fin the heat loss heat is this, but with fin it depend upon case 1, 2 or 3. With fin, which whatever the heat transfer is, for example if we take case 3, suppose for example case 3, with fin how much heat transfer was there? H m into k theta naught tan HML, for example for case 3, and whatever Q without fin is HA theta naught. Then you will find how much the effectiveness is. Cancel theta naught, cancel this A with that A, and now you will find m is root HP upon Ks, and you can write m K by H into tan HML. So when there is no fin is present, only this particular area exposed directly to the air, and in that case Q without fin will be HA, and what is the temperature driving force T0 at the base and T infinity for the air. So without fin the heat is transfer is this, and with fin we can take case by case. For example, if we case 3, then we put this, and if you put value of m is root HP upon K, Ka into K divided by H tan HML, then you find the effectiveness in case 3. You simply can say this case, this H is also the like this, so you say that root Kp by HA into tan HML. This is effectiveness for case 3. Effectiveness for case 3. Similarly, for case 1 or case 2, you can find out the effectiveness of the fin. So this is all about the rectangular fin, we have discussed in this particular lecture 6. So if you are going to conclude this lecture 6, we have seen that how we have discussed the conduction convection phenomena majorly in this particular lecture. In this, we have detailed explanation of critical thickness of insulation, for flat surface as well as curved surface, and second we have seen the rectangular fin. Or application of the fin, and we have in rectangular fin we have also calculated temperature profile, that is theta by theta naught, and also Q loss, and at the end of that we have discussed about the efficiency and effectiveness of the fin. So this is our entire topic, that is lecture 6. The conclusion of lecture 6 is this. Now we have discussed two phenomena of critical thickness of conduction convection phenomena. Another phenomena that is related with the conduction convection is lumped heat capacity system. When the conduction of material is so high that whatever it is internal energy inside that particular material is just convected away in the fluid, that is also related with the conduction convection phenomena, but we will discuss it in the later topic, in the next topic. So far we have discussed the two important aspect of conduction convection, that is critical thickness of insulation and rectangular fins, and we have also discussed what is the application of fins. And whenever you have seen the engine of the motorbike, you can easily see the fins at the engine side. There are wall, that is the fins are like that. If there is a engine, there is lot of fins are like this, so you can easily see the fin. What is the application? To avoid overheating of the material, because overheating of the equipment, whenever there is overheating in the process plant or any equipment, then the system becomes fails, or that equipment could not run further, because overheating phenomena is just like it is saying that your something is going wrong inside that particular equipment, and overheating is not desired in the industries. So to avoid this, this is the helping phenomena for overheating. So in this way we have seen up to the conduction in the particular lecture. So now I hope this lecture is informative for you, and we are going to discuss lecture 7 in the next particular. So thank you so much for attending this lecture. I think that this lecture is helpful for you, and it is informative. Thank you. Okay sir, that's okay.